Okay, all right. Thank you very much, Hugh, for the introduction, and hopefully everybody at all the different sites can hear me okay. I think here, everybody's in the same room, so I think everybody can hear me. I want to thank the Center for allowing me to have this chance to just give a very brief talk about some of the work we've been doing in the Center. It's really the work I've been doing for pretty much over 20 years. Since I went to Merck is where we really first started to develop this kinetic methodology. What I'm going to do today is to tell you about this methodology in the context of an example, or one main example and then a couple others within the center. And really what I'd like to do is to get more, I'm trying to drum up business. We're trying to get people in the center to collaborate more. Most of our work has been collaborative. Well, everything I've done in the center has been with at least 2 different PIs and usually more. But we really would like more people to be bringing kinetics into their investigations. And I'm going to try to convince you of the power of kinetics in mechanistic investigations to get you started, really, is what my real message is going to be, is to do the kinetics first and not last. So next slide. So this is just a slide to talk about the different languages that we speak to talk about reactions. I'm a chemical engineer, and I had to learn to talk to organic chemists when I went to Merck. And so I think that this is a very powerful thing in my career, has been trying to make sure that we, when we talk to each other about science, that we can get on the same page. And we use a lot of different languages when we talk about chemical reactions. You might be someone who does a lot of spectroscopy and tries to understand your reaction through spectroscopy. You might be a computational chemist and you look for transition states, or you draw energy diagrams. Or you might be someone that likes to crystallize an intermediate or find some other way to characterize intermediates. And another language that I think is underutilized in organic reactions is kinetics. Kinetics is another language, another way of describing the work, what's happening in a catalytic reaction. Typically, we look at. Basically, it's just like learning another language. And when you go on holiday to another country, you don't have to become completely fluent in that language, but you need to learn enough of it so that you could order dinner and get a taxi home and just, basically become well-versed enough to make your way around. And I'd like to advocate that for kinetics, is that you don't have to become a kineticist any more than you have to learn how to solve a fast Fourier transform. But you need to learn how to use the tools. And so that's what we're really here for in the center, is to try to bring people into using kinetics more often as a tool. Next slide. The real problem, though, I think that I found with kinetics for organic chemists is that everybody finds it really boring. And I've been trying for 20 years to try to make kinetics more exciting. But organic chemists tend to think kinetics is as boring as watching paint dry. So basically, we've been trying to develop methodology that makes it, actually brings you closer to what the molecules are doing in the reaction. You're not doing a lot of math, you're not doing a lot of tedious repetitive operations, but that basically you can let the molecule speak to you through the kinetic profile. Next slide. So talk a little bit about kinetics and where it all started, really, in catalysis. Was the beginning of the 20th century. The Michaelis-Menten equation, 1913, by Leonore Michaelis and Miss Maud Menten. For those of you who don't know, was the second name in that equation is a women scientist, and it was a really powerful. It was the first time that people had a mathematical expression for what happens in a catalytic cycle. Very simple catalytic cycle. They were talking about enzyme catalysis, but it's the same idea for chemical catalysis as well. A catalytic reaction has to be at least 2 steps. It can't be an elementary reaction. It has to be at least binding of a substrate to a catalyst, followed by reaction. It can be many more steps, but it has to have at least those 2. And essentially, the Michaelis-Menten equation looks at reversible binding followed by reaction. And the Michaelis-Menten equation is it's interesting, the story of how they derived it. That's another whole story. But it really wasn't able to be used very much back then because we didn't have the same kinds of experimental or computational tools. And if you look at the Michaelis-Menten equation, the substrate, concentration, which is S, it's not linear with rate. There's an S in the numerator, and then there's an additive term for S in the denominator. So it makes it harder to use. You can't draw straight lines, and human beings love straight lines. So about 20 years after that, came another development. There were actually several different people that developed ways to try to treat this equation, the most famous of which is a Lineweaver-Burke equation. That was published in JAX in 1934, and all they did was turn it upside down, and now we have 1 over rate, and the expression that you get on the other side of the equation gives just 1 over s on the x-axis, and now we can measure slopes and intercepts. That's why we like straight lines. It's much easier to measure slopes and intercepts and get numbers out of it than it is to measure, to try to look at curvature. And so this was, next slide, this was an incredibly enabling tool. And it basically, generations of scientists were able to extract information from their data because of those simple linearizing operations. And it turns out that that Lineweaver-Burke paper was the most cited paper in the first 125 years of JAX. And if you count the citations, it's cited about once every 2 days. And again, I don't think everybody has read the paper, but they cite it and they know how to use it. And so this is, again, back to my point. You know how, when you learn how to use a tool, you don't have to actually go back through everything that was done to develop it, but it becomes powerful for you to use it. So that was really our inspiration. Next slide. To try to develop, try to think about kinetics for the 21st century. And really in the last decade of the 20th century is when we started to think about that. Basically, we now have things that Michaelis and Menton and Lineweaver and Burke didn't have. We have incredible in situ tools to measure kinetics, much better than they had in the early 20th century. And we have great computational tools. You know, we don't actually have to linearize anything anymore because Excel spreadsheet can find you your Michaelis K and your Vmax in nanoseconds without linearization. But still, the idea, the inspiration that came from having your data speak to you in a way that makes it easier to look at was what we wanted to try to think about. Because if we look at what we do now, this is actually some data when I was on sabbatical in Eric Jacobson's lab, where they were using React-IR spectroscopy, measuring that initial rate, the tiny little box there at the top of the left part of the slide, and then taking that and calculating, you know, that delta C, delta T for that concentration, and making one data point on the Lineweaver-Burke plot. And to get the plot on the right side there, they did that essentially 6 times. And so they threw away all the other data. So basically, I think we can do better. Next slide. So our inspiration really came from thinking about, you know, look at all the data that we discarded. You know, there's information in those data. And I started to think about this as like an interrogation. You're looking at the data and saying, tell me what you know. Some stuff happened, the reaction happened, and we just throw out the data. So what we wanted to do is to try to come up with methodology that would let us use more of the data from any particular reaction. Next slide. So this turned out to be what we call reaction progress kinetic analysis. And we published the first reviews on this, I think, 2005. There's an Angevante and a JOC review there. And then more recently, I published a JAX perspective talking about kinetic profiling. And I'm not going to go through everything that are in these reviews, but basically the concept is that we really wanted to try to find ways to use data from the whole reaction, not just the initial rates, but to take kinetic profiles, which are very easy for us to obtain with in situ tools or even from manual sampling and automated sampling these days. And we want to try to manipulate them in a way that will let the data speak to us, the way a Lineweaver-Burke equation did. And our way of doing this, our interrogation of the data, is going to involve plotting things in different ways and plotting things so that data from different reactions taken under different conditions, they fall on top of each other. And it can be on a straight line or it can be curved lines, but it's a concept of overlay. And I'm not going to do all that today. We don't have time in 20 minutes. But basically the idea is that if there's overlay between 2 different runs, then there's some connection. There's something about the conditions of those 2 runs that is meaningful. And it's what we plot will tell us, you know, what it means. And typically it's going to help us get orders, you know, reaction orders in substrate concentrations. So I'm not going to go into all this, but next slide. This will show you just a flow chart from the Angevante review paper, which is just showing you with a very few experiments. Essentially, you can run 3 experiments, and in that you can know the reaction orders in 2 substrates, and you can know whether the catalyst is robust. That's another feature of this analysis that's not really available in initial rate data, is to know whether your catalyst does the same thing every time it goes around the cycle, whether it's deactivating, whether it's activating, whether it's changing due to something like product or substrate inhibition. So basically, in very few experiments, you can get this information. And this was a real sort of, I think this got taken up faster in the pharma industry because they said, less time, more information, yes. Whereas most professors don't worry about their grad students spending too much time in the lab. They're going to be there 24/7 anyway. But anyway, so it became pretty much embraced by the pharma industry, I think, before academia. But people are realizing now that if you can get more information out of the same data set, why not, even in academia. So next slide. So what I'm going to do, actually, is to talk to you about, I'm not going to go over the methodology. I'm going to let you look at those reviews anytime you want, but I'm just going to take this example of one case that we use this and try to show you how doing the kinetics first gave us the framework for all of the other experiments we're going to do. You know, I'm always saying kinetics are great, do the kinetics first, but kinetics can only take you so far. I'm the first to admit that, actually, that you know, the kinetics can tell me certain things about a mechanism, but it's not going to tell me what the intermediate looks like. It might tell me which substrates are attached to a catalyst in the, say, in the resting state, but I can't figure out the structure. There's a lot of things I can't figure out. But what the kinetics does is it tells you where to look. If it tells you, if you learn something about where the holdup is in the catalytic cycle, you know which intermediates you might go after, which ones not to try to go after. If they're going to be after the rate limiting step, they'll be fleeting, for instance. So I'm going to use this particular example, which we published. I don't think I put the citation on, but it was published in JACS about a year ago. It was a collaboration with scientists at Bristol Myers Squibb on a CH activation problem. So this is the example that we're going to use, and this was studied. It's actually a running project at Bristol Myers Squibb. It took a little while before we were allowed to publish it for that reason. But it's a coupling reaction. It's a CH functionalization. There's a pyrrole and an imidazole, and it's carried out in the presence of an organic base and a pivalate. And it's catalyzed by palladium, like a lot of these reactions are. And they did a ligand screen early on. They screened a whole bunch of ligands, and the best ligand for the highest yield in a fairly high throughput screening came out to be Xanthos. Okay, now that's unusual. That's kind of weird for this kind of reaction. Xanthos is a chelating bisphosphine ligand, and if you look at the structure that's shown on the right side up there, that doesn't really make too much sense for CH activation. If basically we don't have enough space, we don't have enough sites on that palladium to do our reaction. If we're chelating with the bisphosphine, it's going to be tough to do a CH activation. So that was kind of an unusual finding, that Xanthos was working better than monodentate ligands. And that's where they called us in to try to help understand it with kinetics. So next slide. We did kinetics. I'm not going to show all of it, but here's just one plot looking at the concentration of the imidazole substrate going away with time. I think I've got 3 or 4 reactions there. And between that plot and a couple other experiments, really less than 10 experiments, we were able to figure out that it's first order in palladium, it's 0 order in the pyrrole, substrate 1, and it's 0 order in both of the bases, the organic base and in the pivalate. And we had saturation kinetics in substrate 2, the imidazole. That's what I show you here, is that when we increased the amount of imidazole that we started with, the reaction went faster, but only to a certain point. The last two, there's the red and the blue circles, I guess they are sort of collapsing together. When you get up to a high enough starting concentration of the imidazole, you stop seeing an effect of the imidazole concentration. So that's what we call saturation kinetics. Next slide. So with that in hand, with those things in the back of our, started to think about other things that we would want to do. And again, we had this question about the Xanthos. Why is Xanthos working? So the next thing we did was try to do some NMR with the Xanthos, and going from the bottom to the top of these P31 NMR spectra, the palladium Xanthos gives you a nice peak for the Xanthos in the phosphorus NMR. You add the pyrrole, nothing happens. You add the pyrrole and the imidazole, nothing happens. You add the pyrrole, the imidazole, and the organic base, nothing happens. It was only when we added the pivalate base with the pyrrole substrate that we saw changes in the phosphorus NMR. So it clearly needs the pivalate to activate this catalyst system, or this catalytic cycle. So from that, we were able to try to investigate that more. We were actually able to crystallize the species that's formed in that. We basically had a solid crash out, got a crystal structure. Next slide, which turned out to be this species here. We call it complex A, but it helped. This was really the key to opening up this mechanism, because that complex turns out to be a phosphine monooxide of xanthos. It's the oxidative addition of the pyrrole to the palladium xanthos, but the palladium xanthos, one of the phosphines is oxidized. And what that does is it makes that not such a, the chelating bisphosphine, the phosphine palladium bond is strong, but the phosphine oxygen bond is not. So this is now a hemilabile ligand. The phosphine oxide can come on and off as need be for us to do more chemistry on the palladium. So that was a real breakthrough to realize that. And that's actually, in a lot of cases, I think people would stop here and you could write a cycle that would explain everything based on what we knew already. But it turns out that some of the kinetics we did made it seem a little more complicated than this. Next slide. Okay, so the first thing we went back to think a little bit more about the base. Okay, we know that the base got us into the cycle. We couldn't do anything without that pivalate base, right? We couldn't even activate the palladium. But it turns out we also know the base is needed during the cycle. So there's really two roles of the base. And we looked, it may not be easy to see here, but we have, essentially we call it role A and role B. Role A is activating the catalyst. Role B is, the role of the base in the CH activation in the cycle, taking the proton in the cycle. So it turns out that a bunch of bases can do role A. None of the organic bases seem to do anything for either case. But in step B, which is what's happening in the cycle, it seems like only the carboxylate bases are working for us. So that was another key, that we need a pivalate or another carboxylate base to actually complete the catalytic cycle. So next slide. So it's another little piece of information. We sort of gather these pieces of information and try to tuck them together and build a mechanism from it. Are we going to the next? Okay, great. Okay, so this is the start of trying to build the mechanism. We say up at the top left, we've got the palladium xanthos, which with the pivalate gets oxidized. So now we have a palladium, which has got one palladium phosphorus bond and a PO bond. And then we can do oxidative addition to this to make our complex A, which is what's in the box there, okay? So that's what we know so far. We also found out from you can see the kinetics on the left bottom, we actually put complex A in as a catalyst and instead of the palladium xanthos, and it turns out that it's completely competent. It gives exactly the same rate. That's two runs that fall right on top of each other. So that says that complex A is competent. It's probably it probably exists in the catalytic cycle. And up at the top of that graph is another one where we can see that a reaction which was completely suppressed. And that is if we added extra xanthos. Extra xanthos helps to prevent this activation from happening. And actually you make another complex with the palladium xanthos, which we also characterized. So too much xanthos is bad for you. Enough xanthos 1-to-1 with the palladium is good. And that complex A is competent as a catalyst. So next slide. So then we thought that again, you might think you're home free with the mechanism there, but there's a couple other things that don't really fit. I mean, if you can crash out a species and you show that it's active and competent in the cycle, you kind of think it's the resting state. And we had a long argument with a reviewer about this point, but there's some the kinetics told us this can't be the resting state. You've got complex A, you've got substrate, the pyrrole on the catalyst, and now we're going to go through this cycle. But what do we know also from our kinetics? Well, we know that we have saturation kinetics in the imidazole substrate 2. So some step after that species A has to matter kinetically. It can't be the resting state. We also know we have 0 order in the pivalate. So we have a step coming up where something doesn't matter and then where something does matter. And they probably happen in that order. And the resting state is probably going to be something after complex A. Okay, so we go back to spectroscopy to try to look for it. And that's next slide. And we weren't able to crystallize this complex. The reaction is at about, I think it's 95 degrees C. And when we try to crystallize under these conditions where we're adding the pivalate, essentially what we think is happening and what the spectroscopy tells us is that we're doing an exchange for KBr for the K pivalate. Pivalate becomes a ligand, okay? But when we try to crystallize that complex 5 there, V, but it's 5, what happens is we crash out KBr before we can crash out our molecule. So we were not successful, but at least the spectroscopy going from the bottom to the top is adding pivalate to that complex A. And then when you compare, that with what's happening during the reaction, it's clear that the species that forms when we add pivalate to complex A is also in the reaction, under reaction conditions. So we postulated that this complex 5V is where the resting state is, or it's just before we add 2 to the imidazole to the catalyst. And it actually is going to become quite important in the next studies that we're doing, because the pivalate is really a key ligand. I mean, we found out that we couldn't do the reaction with other bases unless they were carboxylate bases. So this type of basis, it turns out to be important in a lot of CH functionalization reactions. Next slide. So what's in red there at the top is just essentially that complex 5. Then the next thing that's going to happen in the cycle is we're going to add the imidazole 2. And we know that we have saturation kinetics from our kinetic studies early on. So that what we think is that's a reversible reaction. And then the species that forms is the one that gets CH activated and goes on to product. Okay, and the other piece of information that was on your slide but I didn't emphasize is that we have a normal KIE. It's not 7, so it's not that the step where the CH activation happens is totally rate controlling, but that's really what saturation kinetics means, is that 2 steps contribute to the rate. You have binding, reversible binding, and then that species goes on irreversibly to product. And that usually gives you a normal KIE, but not as high. You can have, I can't remember what we had here, but you can have 2, 1.5, 2.5 for this kind of situation. So basically, from that step on, when we do the CH activation, we're now past the rate limiting step, and kinetics can't help you anymore, and neither can spectroscopy, because every species after that is going to be fleeting to whatever method that we have to look at. So one thing that we can do if we want to think about the rest of the cycle is computational work. And Martin Eastgate at BMS basically just completed the catalytic cycle. And you can't really see much of it here, but it's really a beautiful story. It's like a ballet, really. We have this hemi-label phosphine oxide coming on and off as it needs to open up a site, coming back down when it needs to, and then the same thing with the pivalate. The pivalate comes on, things rotate to let the substrates in. They're there when they need to pull off the proton. It's a beautiful dance that these computations explain. And also explains the regioselectivity of this. You can't see that too well on this slide either, but it also explains the regioselectivity that we see in the product. So it turned out with this whole combination of tools to give us a really, I think, extensive picture of this cycle. Next slide. And so we could draw the full cycle with all the species that we saw or that we had. Every species that you see there, there's a couple of off-cycle species as well that I didn't talk about. But everybody there has been either seen by one way or another, by kinetics, by crystallization, which is the seeing that doubting Thomases need. People that do kinetics don't necessarily see in the same way. But we have basically computation, spectroscopy, crystallization, and kinetics for every species in the cycle. Next slide. And so basically the next annotation of this slide, next slide. I think it's just coming slowly, perhaps. Are we good, guys? I don't hear anything from Emery. Oh, go back one, please. All right. Yeah. Thank you. So this is just an annotation which tells you how we learned about. I did this actually for the JAX editor when we were trying to say, look, come on, we've really nailed this cycle, you know. And it's just a complete picture of every single species in the cycle and what we did to show that it's viable. Okay. And what I use this for also within the center is to say, you know, we could do this really with any new reaction. We start out with the kinetics, because once we have those kinetic, the rate law, we know where, you know, what else to try to look for. And then we use all the other tools at our disposal. And in the center, we've got people with all kinds of great tools. And this particular example used several, but we've also, in one of the current ones we're doing now, we're using electrochemistry as well to try to show something that the kinetics told us. Computation, spectroscopy, you know, we have a whole range of tools at our disposal that I think the kinetic investigation can provide the framework for. So next slide. hopefully it won't take as long. Because what the next slide is going to do is just to show you three more, just, I'm not going to go through them, but three other investigations that we're doing within the center. And these are all actually, one's finished, one's hopefully nearly finished, the middle one, and then the bottom one is a new investigation. Next slide. And these are all three with Jin Kwan's use systems. Two of them are the monoprotected amino acid ligands. And essentially, in all three cases, right, the first thing we did was establish the kinetics. What are the orders of each of the substrates and the catalyst? Next slide. And essentially what that led us to. And again, those are all stories that could be a seminar, a separate seminar to go through like I just did with the last example. But from the kinetics, which led us to other studies, we were able to learn essentially some important mechanistic information about each system, and then draw the whole mechanism. And then hopefully, really where we want this to go is to help us first understand how these ligands work, in Jin Kwan's case, and then help them design next generation of ligands if we understand what's going on in these cycles. So next slide, I think this is pretty much it. Yeah, so back to that first slide that I showed you about the different languages. Next slide. The way I think about kinetics, which is reaction progress data in this case, is it's like putting the pieces of a puzzle together. When you get the kinetics, you've got these pieces of the puzzle, and you say, where does this one fit? And if you can think of another experiment to do, spectroscopy or something that helps you see where that piece of the puzzle fits. Next slide. Perfect. Okay, so that's just the summary. Is that I'm trying to, again, make the case for how great kinetics is, even if you find it boring. And basically it leads us to the next steps in the mechanistic analysis. And I think that if you do it the other way around, you do a whole bunch of mechanism, and then you do the kinetics at the end, the burden of proof is on you to show that what you've done that's external to the cycle matches the kinetics. The kinetics are the only thing that tells you what's happening inside the cycle while it's happening. So next slide. I think it's the last slide. Just the acknowledgments. This was, like I said, this was a collaboration with Bristol Myers Squibb, and also the center sponsor. Just list of people. Ying was a postdoc who's now at Merck. Eric Plata is finishing up here as a postdoc, and David Hill is working on the third example that I just showed briefly at the end, and he's been working on the second and third examples that I showed. This is scripts. We do get rain. Everybody here knows, but you guys may not know that we get rain. And this was a picture taken a few years ago of a rainbow that went from the top of our chemistry building across the parking lot and landed on the flame of knowledge. I did not see a pot of gold at the end, but I thought it was a nice picture to show. So thank you very much. I'll be happy to answer anybody's questions from the chat room. It's kind of weird seeing you guys here.